guys hear me and see everything okay? All right. These are our day 3 notes. I don't think I'll actually end up finishing them today, which is perfectly fine. I don't want to rush anything because this is the last set of notes for section 3, and then there's a homework to go with it, but then we're done with section 3. So what I'll do is whatever I don't finish today, I'll finish tomorrow in class. And then Friday, I'm not going to make you guys come to a Google Meet. I'll give you Friday to work on this homework assignment. It's posted, but you'll have Friday in class. And I actually didn't even make this one due until Sunday night. So you'll have till Sunday night to even work through these problems, all right? So we'll just see how far we get. We'll finish it tomorrow, and then we're done with this section for the week, and Friday will just be a work on a homework day. All right, so guys, remember, we are in the properties of trig functions. These are all the things that you are and are not allowed to do. So we've gotten pretty deep into what we call the identities, which are statements of equivalence, right? So it's a way to rewrite a problem in terms of another trig function. This is something you could take out, and this is something you could sub in. With that being said, I have to say something. I said something yesterday that was very, very wrong, and after I said that, I was kind of like, I don't think I said that right. So when I went back to the video, guys, I really botched it, and I definitely don't want to be the one that causes any of you guys confusion, so I definitely apologize if anybody was sitting there scratching their heads yesterday. But when I introduced the Pythagorean identities, I told you that they're all dealing with squared trig functions. So I took this off to the side, and I said, guys, cosine squared theta literally means cosine theta times cosine theta, right? Which, then I went on to say, this is where I made the big boo-boo, I said, that is not that. Well, actually, Hardy, that's exactly what that is. So I apologize if any of you were saying, that is that. What I was trying to drive out is what some students mess up, is they mistake this for this. They think it's the angle that is being squared, and it's not the angle that's being squared, it's the cosine of that angle. It's that ratio that is being squared. So in the future, if they write something like this, and you want to think of it like that, that's perfectly okay. They are saying the same thing. Yesterday I said that's not what it's saying, and I'm so sorry. But this is what I was trying to get you guys to believe, is that it's not the angle that's being squared, it is the cosine of that angle, which is a ratio that is being squared. So I am very, very sorry. I actually went and edited that out of the video because I was so afraid if anybody did watch it, I didn't want to confuse them even more. But if anybody saw it yesterday, I'm very sorry. I definitely don't want to be the one to confuse you guys. All right, now let's go. All right, so I rewrote all your identities because we're going to use them today. So I just put these ones up at the top because I want you guys to realize it's not always written like this, but sine and cosecant are reciprocals, right? So the reciprocal of cosecant is sine. The reciprocal of sine is cosecant. So if you ever see this written in a problem, take it out and put sine theta, and vice versa. So I just added those ones because you might see those today in some problems. All right, here we go. There's a couple more identities that I have to show you, but to do the next set, you have to remember what it is to be an even and an odd function. And to be an even or odd function was defined by a function's symmetry. So I just want to review symmetry with you guys real quick, and then we'll go on. So I'm going to move this up so I don't get cut off. All right, that should be good enough, I think. All right, here we go. So, yes, go ahead.
All right, were those equations, the equations, were those equations that you had on the top right, were they just the reverse or what?
Yes, they were. Sine theta is the reciprocal of cosecant, right? So if you reciprocate cosecant, basically if you take cosecant on bottom and put them on top, you get sine. It gets the reciprocal. Okay, so x-axis symmetry. If you took a point xy and you literally reflected it over the x-axis, then what point does it become? It becomes x, the opposite of y, right? When you take a point and flip them over the x-axis, it is the y coordinate that changes. So any function or equation that has symmetry to the x-axis would have both of these points on its graph. It'd have the point 2, 3 and the point 2, -3. Y-axis symmetry. If you take a point xy and you reflect it over the y-axis, well, now the x becomes the opposite. So it's the opposite of x and y. So if any function is going to have symmetry to that y-axis, then both of these points would be on its graph, 2, 3 and negative 2, 3. And then the origin, if you take a point and you reflect it right over or through the origin, then the point becomes the opposite of x, the opposite of y. Both coordinates change to the opposite sign. So any function that has symmetry to that origin would have the point xy and the point the opposite of x, the opposite of y on its graph. Okay, with that being said, even and odd functions, we talked about this way back, I believe it may even have been chapter 1, maybe not chapter 2. But an even function, by definition, is this. It says when x goes into the function, then y or f of x comes out. That's normal function behavior, right? X goes into the function and y comes out. It creates the ordered pair xy. So picture that as 2 went into the function and 3 came out. All right, then it says, and when the opposite of x goes in, the same output, y f of x, still comes out. So when you plug the opposite of x into that function, it still sends the same output out. So if this was saying, now if the opposite of 2 went in, even the opposite of 2 would make 3 come out. That's what it means to be an even function. You can plug x or the opposite of x in, but they both make the same y coordinate come out. That is by definition, the definition of an even function. So guys, both of these points would be on its graph. So that means it's this. That means an even function would have symmetry to the y-axis. An odd function, by definition, said when x goes into the function, y comes out. That's normal function behavior. X goes in, y comes out. So again, 2 goes in, 3 comes out. Then it says, in odd function, when the opposite of x goes into an odd function, then the opposite of y, the opposite of f of x, comes out of that function. So now the opposite of x went in, the opposite of y came out. So now you have negative x, negative y. So then the opposite of x went in, and now the opposite of y came out. That is by definition how an odd function will behave. So if that's true, if these are points on its graph, then an odd function is going to have symmetry to the origin. Okay, so now your next set of identities are called your sign identities. Whether you are taking the sine, cosine, or tangent of a positive or negative angle, there are identities we can apply to this. So guys, all of these problems, I want you to picture theta as a quadrant 1 angle. And I'm going to use an actual angle. I'm going to use 30 degrees. It's a quadrant 1 angle. So because I'm going to use a 30-degree angle, let me give you guys a 30, 60, 90 right triangle to kind of reference off of. Okay, picture this. They're telling you if you take the sine of the opposite of theta. So basically, if the opposite of theta goes into the function, what's going to come out? Guys, think of it this way. If I plugged in the sine of 30 degrees, does anybody remember what the sine of 30 degrees is? The sine of 30 was 1/2. But if I took the sine of negative 30, right? If I took the sine of negative 30 degrees, well, remember what you're really doing is you're taking the sine of a 30-degree angle, but it's in quadrant 4. So what would be the sine of a 30-degree angle? 1/2. But would it be positive or negative because the angle is in quadrant 4? All students take calculus. What is the y coordinate in quadrant 4? It's negative. So now the ratio is negative 1/2. So when you take the sine of the opposite of theta, the opposite of that ratio comes out. So the sine of negative theta is actually equal to the opposite of whatever the ratio was for sine theta. So in the future, if you're ever asked to be taking the sine of negative theta, you can rewrite that as negative sine theta. You can take the negative, basically what you're doing, it kind of feels like you're taking it from the inside and you're putting it on the outside. And that is what you're doing because of what's going on in quadrant 1 compared to quadrant 4. What is going on with that negative theta going in? It's creating the opposite of that ratio from quadrant 1 coming out. Right, and since cosecant is his reciprocal, it behaves the same way. So then the cosecant of the opposite of theta will equal the opposite of cosecant theta. All right, now let's do cosine. Oh, guys, sorry. So if the opposite of theta goes in, and then the opposite of that ratio comes out, is that even or odd function behavior? The opposite goes in, the opposite comes out. That's odd function behavior. That means the sine and cosecant are odd functions. They will have symmetry to the origin. I guess I should say functions, it's both of them. All right, now let's look at cosine. This one says, what if you take the cosine of the opposite of theta? Well, let's do the real theta first. Let's do 30 degrees again. If I take the cosine of 30 degrees, right? That's a quadrant 1 angle. What was the cosine of 30? Root 3 over 2, right? But what if I took the cosine of the opposite of that? What if the opposite input went in? If I took the cosine of negative 30 degrees. Well, negative 30 is in quadrant 4. So remember how that is. You're basically taking the cosine of a 30-degree angle, because that's the reference angle, but it's in quadrant 4. So it would still be root 3 over 2. But what sign is it going to be if it's an angle in quadrant 4? All students take calculus. The cosine of an angle in quadrant 4 should be a positive ratio, because what's the x-coordinate for a point in quadrant 4? It's positive. So now the same positive ratio comes out. So when you plug the opposite of theta into the cosine function, the same ratio still comes out. So now the cosine of the opposite of theta, it'll just equal whatever cosine theta was. It'll have the same exact answer for when you plug the same positive angle in. All right? So if the opposite of theta goes in and the same exact ratio comes out, that's even function behavior. This is an even trig function. And since the secant is his reciprocal, it'll behave the exact same way. The secant of the opposite of theta will get you the exact same ratio that the secant of theta got you. So this is even function behavior. So the cosine and the secant, their graphs will have symmetry to the y-axis. They are even functions. All right, and then last, let's do the tangent. Same thing, let's do that 30 degrees. If I took the tangent of a 30-degree angle, right? If 30 degrees went into the tangent function, tangent 30 is what? 1 over root 3, which cleans up to root 3 over 3. Remember, tangent of a 30, lots of 3's. Root 3 over 3. But then what about the tangent of negative 30 degrees, the opposite of that input? Well, guys, then you'd be taking the tangent of a 30-degree angle, but it landed in quadrant 4. So it would still be root 3 over 3. But now because this angle landed in quadrant 4, all students take calculus. The tangent of any angle in quadrant 4 is a negative ratio. So you're going to get the opposite of that ratio out. So now when the opposite of theta goes in, the opposite ratio comes out. That is odd function behavior. So now the tangent of the opposite of theta will be the opposite of whatever the tangent of just theta was. And since that is his reciprocal, he will behave the exact same way. All right, and again, that behavior makes them an odd function as well. So they will have symmetry to the origin. So the cosine and the secant are your only even trig functions. Everything else is odd. All right, we okay? Again, those are the identities, and then this is how we can use it. A lot of you could sit here and argue, well, I really don't need that identity because you taught me how to do that. The sine of negative 45 degrees is, negative 45 is in quadrant 4. I'm taking the sine of a 45-degree angle, but it's in quadrant 4. I get that. The identity will just give you another way to rewrite the problem, and then you can do it that way. But if you still want to do that the way I taught you, it's going to get you the exact same answer, okay? All right, so let's try it. According to this, it says use the properties of even or odd functions to find the exact value. So guys, basically what they want you to say is, well, if I'm taking the sine of negative 45 degrees, the answer is going to be the opposite of whatever the sine of just 45 degrees was. So now, what is the sine of 45 degrees? Let me get my other right triangle up here for you guys in case you like to use it. Okay, so now the sine of a 45 was 1 over, oh, I did 1 over 1, I'm doing tangent, 1 over root 2, which is root 2 over 2 when you clean it up, and then this says it'll be negative. But guys, this is what I'm talking about. If you just did sine negative 45 degrees, you got a 45-degree angles hanging out in quadrant 4. What's the sine of a 45? Root 2 over 2. What is the sine of an angle that landed in quadrant 4? Negative. It's negative root 2 over 2. So whether you use the identity or whether you just do what I originally taught you to do and rewrite it in terms of the reference angle, you get it the exact same answer. All right, let's look here. Is that a 3? I can't read. There's a blue line going through that. Is that a 3 in this problem? Yep. All right. So if they say take the cosine of the opposite of pi over 3, well, according to the identities, the cosine of the opposite of this angle would just equal the cosine of that angle, right? Cosines are even. The cosine of the opposite of theta is going to get you the exact same answer, whatever the cosine of theta was. So now all you have to do is take the cosine of pi over 3. Pi over 3 is 60. So here's your 60. The cosine is 1/2. But again, if you did this the way I originally taught you, negative pi over 3 is hanging out in quadrant 4. So you're taking the cosine of a pi over 3, but it landed in quadrant 4. Cosine pi over 3 is 1/2. What is the cosine of an angle in quadrant 4? It's positive. So either way you do it. These help you more so when we're trying to simplify trig expressions. It's just a way to rewrite something in the problem. All right, cotangent negative pi over 6. Well, being that cotangent is an odd function, the cotangent of negative theta is going to equal the opposite of whatever the cotangent of pi over 6 really was. So guys, cotangent pi over 6, that's the cotangent of a 30. So come over here. Cotangent of a 30 is what? A over O. It's root 3 over 1, so it's root 3. And then the property says it'll be negative root 3. But again, at the end of the day, negative pi over 6 landed in quadrant 4. You'd be taking the cotangent of a pi over 6 that landed in quadrant 4. And what is the cotangent function? All students take calculus. It's negative in quadrant 4. Okay, keep going. Are we okay? Is everybody all right? Oh, baby. All right, the tangent of negative 37 pi over 4. The tangent of the opposite of theta, guys, it should equal the opposite of whatever the tangent of just 37 pi's over 4 were. Where the heck do 37 pi's over 4 land? Let's figure this out. Guys, we're working with pi's over 4, right? So that means if this is pi, that's 4 pi over 4. And then another is 8 pi over 4. There's your 2 pi. So 37, right? So let's do this. All the way around is 8. All the way around again is what? 16, right? Another 8 pi's over 4. Go around again. Another 8 is what? 24. Another 8 is what? 32. I'm getting there. Another 4, another half a rotation gets you to 36, making the 37th right there. 37 pi's over 4 land in quadrant 3. So what is the tangent of 37 pi's over 4? Your reference angle is 1 pi over 4. So you're really taking the tangent of a 45-degree angle that landed in quadrant 3. So what is the tangent of a 45? 1 over 1 is 1. And then this says it'll be negative. So now, pretend you got, just pretend tangent was negative here. So then that was negative 1. That would make it negative 1, and your answer would be positive 1, okay? All right, you guys try E. What is the cotangent of negative 3 pi over 2? Again, you could do that as is, but the property says you can pull out the negative and do it with a positive theta. These are one of the ones that I definitely use my unit circle for because it's quadrantal. Right, the property says the cotangent of negative 3 pi over 2 will be the opposite of whatever the cotangent of just 3 pi over 2 was. So here's 3 pi over 2 sitting at the ordered pair 0, negative 1, right? Cotangent is the reciprocal of tangent. So if tangent's y over x, sine over cosine, this is going to be x over y, cosine over sine. So x over y is 0. That makes it negative, but there's no such thing as negative 0, so it's just 0. All right, you guys do the last one. What is the cosine of negative pi? Again, you could do that just the way it is. Go to negative pi, get your x coordinate, be done. Or you could do what the identity says to do. Remember, cosine's the only even function. So it says if you have the cosine of the opposite of theta, that should just equal the original cosine theta, which is cosine pi, which is another one of your quadrantals. So I use my unit circle for this. There's pi radians, which, guys, negative pi sits in the exact same place. And the x coordinate is cosine, so it's negative 1. How do we feel? Everybody okay? Again, if you ask me, when we're doing problems like this, I don't use the identities. I really don't. To do them this way is not my go-to method. I would literally just go to where negative 3 pi over 2 landed and take the cotangent. I would figure out where negative 37 pi's over 4 landed, get my reference angle, and get my ratio. But the identities say you can rewrite, all right? I use the identities more for problems like this when we're really simplifying these trig expressions, not just finding sines and cotangents of those angles. So if you're sitting here saying, I really don't need that, you really don't, being from what I've already taught you. However, this will come in handy when we start looking for ways to rewrite the expressions, okay? I think I'm going to stop there. Just because why rush it? I have tomorrow to get through any of this. I'm giving you Friday to do your homework. Your homework ain't even due till Sunday. So I think I'm going to stop there before I even go on any further. All right? So if any of you do, I did post the homework on this. If any of you do open it, I haven't taught you everything yet, so just you do what you want to do though, okay? All right, so like I said, I think you have Monday's homework. The day 1 is due tonight. Yesterday's homework is due tomorrow, and then this one I didn't make due until Sunday. Or did I make that one due Friday? I don't know. You'll see the due dates, all right? But here we go. If you have any questions, please let me know. Otherwise, after I take your attendance, you will be free to go.